So, we're going to begin studying relativity. A word of warning here. So far, many of the things you've learned seem to agree with our common sense. The common advice after you've had a go at answering a particular question is to think, does my answer make sense? Does it agree with my everyday understanding of how things should behave? You should still continue to do this, of course. If you calculate the distance moved by a bowling ball in a mechanics problem, for example, to be 10 to the minus 20 meters, you know you've probably done something wrong. But the physics you're going to be learning now won't necessarily agree with what your common sense tells you should be true. You'll learn, for example, that time can slow down, distances can contract, the mass of an object can increase. These are not just optical illusions. These phenomena really do occur. This is really how nature works. But they'll seem very far removed from our everyday understanding of how the world works. And when you come on to studying quantum physics, you'll find even stranger things. Waves that can behave as particles, particles that can behave like waves, and solid objects that can pass straight through each other. So you'll need to get comfortable with the idea that your common sense may fail you. What appear to be the laws that govern our everyday lives are only part of the story. So we're going to start with Galilean relativity. Now, the idea of relativity isn't a new one. The ideas of relativity actually go back to Galileo, or possibly even earlier. We'll get on to Einstein's special relativity later. But before we do that, we need to make sure that we understand Galilean relativity, common sense relativity, if you like. We began to look at this briefly in the topic of collisions in mechanics, but we're going to think a little bit more carefully about it now. Relativity in the next video. But for the moment, we can note that 1. A reference frame extends infinitely far in all directions, and 2. All the experimenters are at rest in their reference frame. So, the reference frame in which you're sat watching this video could consist of a coordinate system in which you're sat at the origin, with x running off to the right of you and y pointing vertically, and a z-coordinate at right angles to these two. It's not necessary for you to be sat at the origin. You could be sat at some other coordinate in the reference frame, but it's just more convenient for this example to place you at the origin. And you can locate your mug of tea off to your right, and you can specify the x, y and z coordinates of the mug of tea in this coordinate system. And there's the window over there at some different x, y, z coordinates, and so on and so on. In the language we used to define a reference frame, you're an experimenter, in inverted commas, measuring positions in a particular coordinate system, and, later we'll see, also times. Here's a sketch of the coordinate system. We've left out the z-coordinate for clarity and added a symbol s. We'll refer to that from now on as the s-coordinate system. Then imagine our window faces out onto a train track, and as we watch, a train goes by, and there's someone on the train, Bob, who happens to look at you as they go by, and they see you, and the chair and the mug of tea and so on. Bob, on the moving train, is in a different reference frame. He uses a different coordinate system. We'll call that the S' reference frame, and we'll place Bob at the origin of the S' reference frame. Again, he doesn't have to be located at the origin, but it's just more convenient for this example. In the reference frame that Bob is in, he's got a sandwich in front of him, about 10 centimetres away, and there's an annoying person talking very loudly on a phone about 2 metres in front of him, and so on and so on. If Bob wanted to measure the position of the sandwich for some strange reason, he'd measure the x-coordinate of the sandwich to be 10 centimetres. We'll, however, add a prime symbol to Bob's x-coordinate to distinguish it from our x-coordinate. X prime is 10 centimetres. And again, using the language we use to define a reference frame, Bob is an experimenter, in inverted commas, also making measurements of position, but now in the S' reference frame rather than the S reference frame. Now as Bob looks through the window into our room, he sees us, and the mug and the chair and so on. Measured in our S reference frame, the coordinates of these objects are unchanging. But measured in Bob's S' reference frame, the coordinates of these objects are changing with time. The x' coordinate of the mug of tea starts positive, meaning that it's ahead of the train, and then Bob passes by and the mug of tea recedes behind him, and the x' coordinate becomes negative. And in the same way, in the S reference frame, the x-coordinate of Bob's sandwich is initially negative. It gets closer to us, and then it disappears into the distance. The x-coordinate of Bob's sandwich becomes positive, and it keeps increasing with time. In relativity problems, we often imagine things like firecrackers or lightning flashes, sudden things that happen at a well-defined time and place. Sticking with the train analogy to the bitter end though, we'll say that a mobile phone suddenly rings on the train. And the phone is about 2 meters down the train from Bob, x prime is 2 meters, and it rings 10 seconds after Bob has passed us by. T is 10 seconds. And since the train is moving forward at velocity v, the x-coordinate of that event is, in the S reference frame, x equals x prime plus vt. Vt is how far Bob has travelled down the track from us in time t, and x prime is the position of the mobile phone in the S prime reference frame. The y and z positions are not changing, of course, because the train is moving in the x direction, and the times are the same in both reference frames in Galilean relativity.
In this video, we're going to consider length contraction, space-time intervals, and the Lorentz transform. But before we get into the detail of that, I'm going to ask you a question on proper time, which will help us recap some of the material from the previous video. So we have a rocket making a trip, leaving the Sun and arriving at Saturn. We have a reference frame S, which is that of the solar system, so in which the Sun and Saturn are fixed, and the reference frame S prime, which is that of the rocket, in which of course Saturn and the Sun are themselves moving. So the question is, in which reference frame is the time interval between leaving the Sun and arriving at Saturn a proper time interval? So pause the video now and have a think about the problem. Okay, well hopefully you recalled from the previous video that a proper time interval occurs if the two events occur at the same place in the frame of reference. And of course that's true for the S prime reference frame, which is moving at the rocket. Leaving the Sun and arriving at Saturn occur at the same place in the rocket's reference frame. So the answer is option 2. Okay, let's use the example we've just considered to think about length contraction. In the reference frame of the solar system, in which the Sun and Saturn are fixed, the rocket travels a distance L in time delta t. So we can write the velocity of the rocket v as just L divided by delta t. In the rocket's reference frame, Saturn moves a distance L prime to the rocket during the journey, and that occurs in a time of delta t prime. Now we know that the time interval in the rocket's reference frame is a proper time interval, so delta t prime equals delta tau. So we can write the velocity as just being L prime over delta t prime, or L prime over delta tau. Now in the previous video we deduced a relationship between the proper time interval delta tau and the time interval delta t in a reference frame moving relative to it, which was just that delta tau equaled delta t times the square root of 1 minus beta squared. So if we substitute for delta tau in here and then rearrange, we get the fact that L prime equals the square root of 1 minus beta squared times L. Now the factor root 1 minus beta squared is always less than 1. So L prime is always less than L, which tells us that a moving object is shortened in the direction of movement. This is Lorentz contraction.